Good afternoon, everyone. People are starting to log in, so we got a few minutes here, and we'll get started in about three or 4 minutes. We'll give everyone a few more minutes to log on, and we'll get started at the top of the hour. All right. Well, it's the top of the hour, so we're gonna get started. Thank you, everyone, for taking the time out of your busy schedules to join us for Designing with Undercut Mechanical Anchors. My name is Zach. I'm part of the marketing organization here at DEWALT. And our presenter today will be Lars Anderson. He's our field engineer in the Pacific Northwest in Northern California. Lars will give a little introduction to himself here in a minute. I just wanted to go over a few kind of housekeeping items. If you have any questions, please use the Q&A function at the bottom of the screen to type your questions. We do have a few panelists signed on that will be answering questions while Lars is presenting, if they are able to. And then, of course, at the end, we'll have a live Q&A session where our other panelists will come on to video and answer any questions that may come up. This webinar is accredited with NCSEA for 1 PDH. So the normal rules apply for this webinar. If you stay through the majority of the webinar, we will send out a certificate that you attended, most likely tomorrow or the following day. So you will get those. And we will also send out a PDF version of these slides so that you will have them for reference if needed. With that, I think that's about all the housekeeping. Lars, I'm going to turn it over to you, and we're looking forward to the presentation. I'm going to go off camera. Take it away, buddy.
All right, thanks, Zach. Hey guys, yeah, my name is Lars Anderson. I'm the local field engineer out in Northern California in the Pacific Northwest regions. A little bit about me. I graduated from the University of Colorado at Boulder in civil engineering. Then I kind of stayed in Colorado. I worked for a heavy civil general contractor as a project engineer. I worked as a project engineer out in the central coast of California for a general contractor as well, doing heavy civil work, bridge building. And then see below, I was a structural design engineer, worked at a firm locally in the central coast of California. And then I was an assistant project manager for an architectural precast concrete panel manufacturer. Kind of got introduced to the San Francisco Bay Area, the different regions around Northern California. And then I've been with Stanley Black & Decker DEWALT for about a year. I joined back in January of last year. I live in Santa Cruz, California. I don't know if anybody of you guys have been out here. It's a beautiful city. So in my free time, I like to play the cello. I played for about 24 years. I like to go surfing, hiking, just hanging out in the city, enjoying the nature as much as I can. So bear with me too. My neighbors just decided to renovate their deck this week, so you might hear some saws and some pounding in the background. So if that's an issue, let me know for the audio. But hopefully I'll talk loudly and go through this presentation pretty smoothly for you guys. So the agenda for the undercut anchors: learning the objectives. First off, just learning what an undercut anchor is, why undercut anchors, specifically how they differ from other anchors that you're aware of, screw anchors, wedge anchors, etc. Some design qualifications for the undercut anchor, undercut anchor systems, how they interact, also installation procedures, kind of step-by-step guides, and also a visual better understand how the undercut anchor is installed. And then some use cases. Some of the cases I actually worked on directly, so it's pretty cool to see. I have some pictures to show you. Learning objectives, getting to that. Yeah, same thing as last slide. Understand undercut anchors, the critical connection behind the undercut anchor. Know the difference between the different types of anchors versus the undercut. Anatomy design, installation, design considerations, compliance. That's also key. I'll talk about later. Real world case studies. So as we get into undercut anchors, they are the only post-installed anchor that utilizes bearing to transfer loads in concrete. Here's a selection of other anchor types. So at the top, casting place head bolt that uses a bearing connection in the concrete. However, that's prior to the pouring of the concrete slab, wall, etc. You see the screw anchor below the undercut is using a keying type of frictional force. So yeah, as you screw in the screw bolt that we have or a similar product, it uses the external threads to key into the concrete, creating that frictional force and tension. And so as you see the expansion anchor below, it uses a bolt. There's two different types: a sleeve expansion anchor or a bolt expansion anchor. But it uses a wedge clip at the bottom of the hole. That wedge clip expands outwards, creates a frictional force on the inner lining of the hole, of the wall of the hole itself, and that produces the force needed in tension to resist. And then the adhesive anchor using epoxy or acrylic. This is a bonding type of force, and this bonds to the inner lining of the hole wall. It also bonds to the threads of the threaded rod, or it bonds to the ribs of the rebar for a post-installed rebar application. The epoxy or acrylic bonds to the concrete or masonry base material, depending on application on site. But in essence, the undercut anchor is different. It uses a bearing force. It's a post-installed anchor. And so the bearing force is applied deep at the bottom of the hole. The bearing, in essence, how I view it, is just the distance from the back of the expansion sleeve splines, as you see there, kind of wrapping over the cone. That distance to the face of concrete is pretty much the bearing, the total bearing distance that is needed to apply throughout the concrete for a overall bearing load pull out. So I mean, imagine trying to pry out X amount of inches of concrete. It's very, very hard to do. And so that's why the bearing force is ultimately the strongest force for a post-installed anchor over the other types of anchors. We can talk about this later too. Here's a nice visual description, and it's just a nice graphic. We'll have a video of this graphic too later on. But yeah, again, utilizes bearing, which makes them the ultimate post-installed mechanical anchor available out there on the market. Loads are transferred. You can see that force is kind of outwards, direction outwards, like a diagonal angle. And then so there's that distance I'm talking about from face of concrete to where those sleeve splines are on the back. So huge amount of load. It's very hard to pry out, almost impossible to pry out one of those things. So we'll get into the anatomy here. Anatomy of the undercut anchor. The expander cone itself at the bottom left is connected to the anchor rod, which is a fully threaded rod, not partially threaded, fully threaded rod. This anchor rod is available in A36, B7, and stainless steel 316 grades of alloy. The 316 stainless steel is great for corrosive environments, very highly or widely used, a lot of wet conditions and wet environments, specifically up in the Pacific Northwest. Very useful. You see the expansion sleeve spines, as I was telling you about earlier. These are connected to the expansion sleeve. It's one unit. And then those splines will eventually expand over the expander cone when the anchor is properly set. The expansion sleeve is used and it allows for a ductility of the anchor rod itself, which is very key. And then also the washer and hex nut above is used to set the anchor and to do a final torque of the anchor as well. So use a torque wrench for that. There are two types of undercut anchors. There's a preset version and through bolt version. On the left, you can see there's a lot of dimensions, description of how the preset is installed within the concrete, basic concrete, and then you see the through bolt version on the right side. So as we go on the left, the preset version is with the sleeve of the anchor flush with the face of concrete. As you see right there, it's just below the fixture. On the right side, the through bolt, the sleeve of the undercut anchor extrudes up and actually is flush with the face of the fixture or base plate, whatever type of fixture or mounting that you have above the face of concrete or face of masonry or whatever. But usually face of concrete is exactly where the expansion sleeve will extrude up through to. This increases the shear load capacity, as you would imagine. So as the steel of the fixture, there's a horizontal force applied throughout the base plate or the steel fixture, or maybe even in a seismic condition, that steel is going to interact with that sleeve spline or the sleeve itself of the anchor. And this increases the shear capacity as steel interacts with steel. Whereas in the preset version, you have steel interacting just with the anchor rod itself and not with the sleeve. So you get a little bit more shear load capacity, about 40% greater on average between the preset and through bolt version. So if you look in certain load tables in the ICC report, you'll see kind of a difference in shear load capacity, about 40%. So if you're designing for a higher shear demand, look into the through bolt version, especially if you're doing anchor or equipment mounting and working within a high seismic zone too. Maybe look into a through bolt version as well. It can be a little bit difficult too if you are choosing a through bolt. Maybe on site you have different fixture thicknesses, etc. You want to make sure that that sleeve is flush with the face of the fixture. So if the fixtures are differing in thickness all throughout the site or in different applications, maybe it is best to just use preset and just to have that sleeve flush with face of concrete. So just kind of note the two different versions there. And then as far as undercut, it is possible for the sleeve itself to be tweaked in the dimension itself. So if there is a certain custom application, that sleeve can be set to a certain fixed length as well. There are standard manufacturer sizes. However, that sleeve length can change, as well as the overall anchor rod length too. So if you guys have questions about that in the future, reach out to me or my team and we can talk about it more. So why design with undercut anchors? They do not fail in pullout because the load is transferred deep into the concrete by the solid bearing at the end of the anchor. The load is controlled by concrete breakout or steel failure. You don't find usually pry out a main factor in the failure of the anchor itself. It's usually controlled by concrete breakout or steel. That's because just of the deep embedment that's going on in the slab or the wall. Pull out very hard for undercut anchor, and you only see concrete breakout or steel. And we'll look at design examples later on here in this presentation, kind of showcasing those two specifically. The unique design of the undercut anchor facilitates the yielding of the rod along its entire length, resulting in a pronounced ductile behavior and deformation capacity. So you see this graph here, undercut load versus displacement. You'll see the top left of the graph there, you see AA, that's an adhesive anchor, and steel failure. You'll see it is loaded pretty high. However, the anchor displacement is very small. So when you get that steel failure rupture, get a loaded displacement. Now, if we look over to the EA-S, that's an expansion anchor. That's actually a sleeve expansion anchor, and that's controlled by concrete failure. That's what they have in parentheses. This gets loaded to a pretty high load, can be, and it also gets to a generally overall good displacement, anchor displacement. However, that curve is slightly smaller than what you would get for a adhesive anchor. You also see the SA, that's a screw anchor itself. So internally threaded or externally threaded screw anchor right there. That gets loaded somewhat high, and then also has a really small displacement. And then also you see the EA-B, that's an expansion anchor. That's a bolted expansion anchor right there. It's controlled by pull-off failure in this case. For this, you can't really load it that high, and you also generate a high displacement for that. So that curve is very long and lethargic in a way. So the ultimate anchor to use is the UA, so the undercut anchor. Has a high load. It's the stiffest and one of the strongest anchors out there. Can it be immediately loaded too? Unlike adhesive anchors where it has to set, you have to do working jail time and also wait for the cure time to happen before you can load that anchor properly. Undercut anchors have greater ductility and tension than other mechanical anchors too. The anchor rod can actually displace and have kind of a stretch to it. So some other anchors can't. The screw bolt, like the screw anchor, can't. Yeah, so just kind of a good graphical representation of why undercut anchor outperforms the rest of these different anchor types. These anchor, because of load transferability too, these undercut anchors are sold at a premium price compared to other wedge, screw, or adhesive anchors. Undercut anchors are typically used on complex and demanding projects, such as water treatment facilities, water treatment plants, industrial warehouse buildings, transportation jobs such as tunneling, rail lines, bridges, heavy interchanges, etc. Something that requires large tensile loads or hanging of large equipment. If you guys saw the first slide, and the first slide of the presentation, hanging those fans and that kind of exhaust ventilation fans underneath in the tunnel. We use an undercut anchor for that application. So large equipment that's hanging, high tensile loads, usually used in seismic applications, very important. Undercut anchor is approved. At least all undercut anchor is approved in seismic applications. So in utility systems, use widely utility systems, equipment mounting, large equipment storage handling, anything with a strong structural connection in general. Something that you have to generate a high tensile force from, and you can't do that with an expansion anchor or even an adhesive anchor, something greater. Definitely look into an undercut anchor, as these will be more common in future years to use. So for installation, complete undercut anchor system ensures that the undercut anchor performs as designed. So this incorporates a rotor hammer, incorporates a dust extraction vacuum. So that's OSHA Table 1 compliant. It's a HEPA vacuum, which sucks out silica dust. Very important that the hole is cleaned too prior to placement of the anchor. So it's paramount that you use a some sort of extraction vacuum to suck out that dust. HEPA vacuum, Table 1 compliant OSHA is widely used on most projects here on the West Coast and also around the country. We also For this undercut anchor, use a hollow stop drill bit, or you can use a standard stop drill bit. The difference between a hollow and standard is that the standard, this drill creates dust. The hollow actually is attached to the vacuum system. And while the drill is drilling, you'll see this in a visual here soon. While the drill bit is drilling in the hole, that dust is extracting out through the hose there, the hollow bit, and going into the vacuum. Then the undercut actually uses an undercut bit, separate undercut bit and the stop drill bit. This undercut bit actually carves out the cavity in the back of the hole, which you'll see. This can be also a hollow bit, or it could be a standard bit. So hollow just means it's hooked up to a vacuum, sucks out the dust. And then also, as you see, you use a setting sleeve. This could be a powered setting sleeve, which is a SDS Plus, SDS Max attachment to the rotor hammer. Or you can use a manual setting sleeve. This setting sleeve is just used to set the anchor properly in the hole itself. The setting sleeve actually comes face and actually flush with the sleeve of the anchor. So the setting sleeve brushes up against the sleeve, pretty much a pounding effect, the chiseling effect, setting that anchor into the hole properly, driving those sleeve splines over that cone, which you'll see here. Next slide. The torque wrench is the final torquing of that nut, similar to kind of what you see in expansion anchor. You do a final torque to a specified torque rating. This can be found on an ICC report, and you torque down to a specified load. So I'll play a video here, then I'll pause it because we do have some audio kind of quality issues on this video. So I'll just pause throughout the video. So as you see here, we have the stop bit. The stop bit is drilling through the initial pilot hole. And then as you see, it's a hollow bit itself in this visual. So this is extracting the dust out as it's drilling through the hole. The hollow bit generates lower friction, lower heat as it drills. So the wear and longevity, the wear and tear is less on the bit. And the longevity, it can be used more than a regular standard bit itself, standard stop bit. There are two holes in the front of the bit, as you probably saw, that allow for that air to go through the bit itself and for that dust to actually pass through the entire bit itself too into the vacuum. Here's the undercut bit, kind of a cool visual. This incorporates cutter blades and a bow jaw. Call it that cutter blade pretty much expands out and carves out the cavity in the back of the hole. It also has a hole in the front, as you see there, which allows the dust to get sucked through the front of the bit all the way to the vacuum. All right, so if you see right there, the cutter blade, they're carving out that cavity. It's more kind of like a conal shape, the back of the hole there. It's a little bit wider diameter, as you see the initial stop bit diameter. This creates that cavity, and with a hollow bit, the hollow drill bit itself, the undercut bit, you can suck out that dust in the back of the hole, which is really key, paramount. If you don't have, if you have dust at the back of the hole in that cavity, it is hard to set the undercut anchor properly. That dust will compress, or some of that concrete dust might compress. The anchor might get dislodged slightly, and you might not get the intended embedment depth from your anchor. Here we use the setting sleeve. That's, as you see below, it comes in flush with the face of the sleeve itself of the anchor, and then you just use a chiseling method to pound the sleeve and the sleeve splines over the cone, as you'll see. And then here, this is a red indicator marking on the anchor rod itself. This is predetermined and manufactured as a preset line. based on testing, which shows visually the required embedment depth and also shows you that the anchor has been set properly. This should match face the concrete, and also should slightly just appear above the sleeve itself, the sleeve of the anchor. So again, kind of step-by-step installation. You see that the initial stop bit, you drill the hole, then you clean the hole out, either with the hollow system or just the standard. If you're using a standard bit, make sure you have a vacuum extraction system to suck out that dust properly. Make sure you clean that hole, and then use the undercut bit, which creates that cavity at the back. Make sure that dust is properly sucked out. It's really important that second process is the dust is sucked out entirely. Now, so you insert the anchor, you drive that in, powered, or you use a sledgehammer. The powered version's better with the roto hammer, I would say. Sledgehammer is pretty hard to do, and there's actually a picture I'll show you later. And then the sleeve spline will be flush, so the sleeve splines will extend over the cone, and the sleeve itself will be flush with basic concrete in the preset version. And then you do the final torque in it. Moving into design considerations. As a design engineer, you want to take into account the ICC approval, ESR reports, undercut anchors. Our undercut anchor has an ESR report to it, 4810. And ASTM standards, you want to take into account ANSI drill bit standards as well. Anchor spacing, edge distance, seismic cracks or uncracked concrete conditions for your project, steel grades and steel finishes. So also take into account IBC codes, local building codes too. Different jurisdictions might have slightly different terminology. So for anchor design, we're getting into 6 different modes of failure. However, we're only focusing on 3. And like I said earlier, pull-out isn't really a factor for an undercut anchor. It is when you look at an expansion anchor. But we'll focus on steel failure, concrete breakout, tension. And so for ACI 318, Chapter 17 is what we look at for anchor design. And we want to make sure that this interlocking system prevents the anchor from pulling out. And so the undercut anchor, it results in high load capacities and small displacements. As you see, there's a nice visual on the right, shows that anchor properly set, ready to be used with that fixture on top. So as we look in ACI 318, chapter 7, this is 318.19, and this is table 17.3.1. But you see here that there's 2 failure modes. And so the general rule is that the nominal tensile force multiplied by a phi factor is greater than the ultimate tensile force. So the capacity is greater than demand. So we have steel failure, and we have concrete break on the right. In this case, we're using a 1/2 inch diameter, our CCU plus anchor undercut. It's a grade B7. This is ICC approved. So as we get into steel capacity, we're testing steel strength and tension. We go into code, we look up from the code itself that this equation is the nominal tensile force. And so we have to use the cross-sectional area of the steel of the anchor, ASE, multiplied by the ultimate yield strength of the steel itself, FUTA. So we get 17,750 pounds tensile force. Now we have to go back in the code, look up phi factor for ductile steel elements. This comes out of chapter 17, 0.75. We multiply that by our nominal tensile force, you get 13,310 pounds. Now, a little bit more complicated, we look at concrete breakout capacity. This is dictated 17.4.2 in the code. We look at NCB, so the nominal concrete breakout strength. Now, the projected concrete failure area of a single anchor in tension, ANC, and also ANCO, that can be crossed out to 1. But for this example, we'll negate that out. The area, projected area over the projected area based on edge distance. In this condition, we'll say it's 1. We also, the different P factors, the 5 factors, so breakout capacity, breakout cracking factor capacity, breakout splitting factor, breakout edge factor. Those 3 factors we can just put to 1, set to 1 for this condition. We're only focusing on NB, it's the nominal breakout, which key to note, the KC, this actually is a effectiveness factor, the anchor in concrete. KC is 24 in this case. There's a slide I'll show you a little bit later. Usually, based on testing, for other anchor types, it is actually 17. So most notably for the undercut anchor, KC is 24, which does increase that nominal breakout strength. F prime C, 6,000 PSI in this case. We're also doing Landum A, 1.0. HE effective is just the effective embed depth of this undercut anchor, 5 inches. So we multiply that out. We get nominal strength 20,785. And we go back in the code. We look at chapter 17.3.3, so 17.3.3, and we look up the tension loads, concrete category 1, condition B in this case. We find our phi factor, so 0.65 is our phi factor that we multiply by this NCV, 13,510 pounds. So as we compare the two, we find that steel failure controls slightly, about 200 pounds less, but overall steel failure controls in this case for this undercut anchor. So that's pretty large, 13,000 pounds for the undercut anchor. This is a 1/2 inch diameter. So as we look at the KC factor, effectiveness factor, you'll see here on the different tables in our ICC reports for different anchor products. We have 24 for the undercut anchor. This differs from the expansion anchor, the screw anchor, and the adhesive anchor. All these are set at 17. So another Y undercut anchors. We have ductility requirements for anchors, as mentioned in ACI 318. There's different clauses. So as we get into this, because of extreme low capacities, high performing undercut anchors can be designed for ductile steel capacity, provided they're embedded deep enough to prevent concrete breakout. So according to ACI 318, for a single anchor to qualify as a ductile connection, there's a number of criteria that have to be met. Oh, apologize. And the first is the ductile connection definition of ductility, which is generally defined in Chapter 2 of the code. So requires elongation of 14%, reduction in cross-sectional area of 30%, which that does meet. The undercut anchor does meet that criteria. It can be elongated 14%, the reduction in cross-sectional area about 30%. Within Chapter 17, a ductile anchor is also considered when there's a 20% margin of safety between the nominal steel and concrete strength. So you get that 1.2 times the nominal strength. It's less than the governed strength, concrete governed strength. So that's checked off as well. That meets the requirement. Also, the anchor is designed to be the main source of energy. So if the undercut anchor is to be the main source of energy dissipation, a stretch length of 8 diameters is required of that rod itself. So as well as restraint against any buckling, and regularity over the length is also necessary. So the embedment, geometry, and external sleeve of many undercut anchors achieve these specific requirements. The regularity is due to the fact that the anchor rod itself is fully threaded. If you have a partially threaded rod, buckling might look different in testing, and also the regularity might not be constant and uniform throughout that steel profile. So keep that in mind. It's very, very important that the anchor rod is fully threaded. It's consistent throughout the entire length. So you see here, there's 2 different illustrations. ACI 318 free stretch length talks about this. So the stretch length here provides two possible solutions, and the far left one illustrates a headed stud embedded in the concrete with additional stretch length achieved via anchored shear setup. And the second example in the middle shows another headed stud with the debonded section at the embedded end using a sleeve. So the more elegant solution would be an undercut anchor itself. You don't need that anchor chair. Now, if you're working with a kind of a small slab, a thin slab, you might need to use an anchor chair setup to allow room within that thickness of the slab for your cast in place anchor or whatever have it, right? Or expansion anchor. The anchor chair is a pain to set up, very time consuming, tedious. Now, if you're using a debonded section, you're trying to get deeper to get the ductility. It's also more time costly and effective to achieve that stretch length. A little bit more painstaking. And so using the undercut anchor, it's most effective. It has that stretch length, achieves that stretch length, and it's a post-installed anchor. And so you don't have to drill that deep. Just achieve your effective in-bed depth. So it can work in more or so thinner slabs than intended if you're using it like using the middle illustration there. Using a debonded section, you have to go deeper. As far as compliance, there's a variety of U.S. legislation covering different aspects of domestic material requirements in the building environment. For example, the American Iron and Steel Act, Buy American, and Trade Agreement Act, Buy America covering DOT and federal highway funded projects, and most recently the Build America, Buy America law signed back in 2021. This anchor is fully compliant with all of these. It's important to understand that the level of domestic material requirement for each project, and manufacturers have information available to help you navigate these. As you see here too, the middle, there's a chart, conformance chart, presented by DEWALT here. There's an updated chart that we have now that is available upon request. It's soon to be online on our webpage. So if you guys do have questions about the updated conformance chart, let us know. We can send you that. But this is more of an older picture here, and it's on our presentation. So then again, just to kind of reiterate common project types, these undercut anchors are used on water treatment plants, DOT projects, federal buildings, military projects, infrastructure projects. Kind of rule of thumb that I think of is a project's federally funded by a government entity, chances are it's gonna fall under one of these categories, if not all, most of all the categories here, Buy America, AS compliance, etc. So the undercut anchor is very effective in meeting all the specification requirements for a job. Here, I'm going to show you a comparison between the undercut anchor and the cast in place anchor, headed stud, and then also a expansion anchor. And I'm using our proprietary software, DEWALT Design Assist, to do that. Keep in mind, there is a seagull in the background. I live in Santa Cruz, and I was recording this video. There was dirt in the back, so it's annoying. I apologize. But here's kind of a good visual kind of comparison between three different anchor types, kind of outline why the undercut anchor is so powerful and effective. As you can see here, I have normal weight concrete, 4,000 PSI, 12 inches thick slab. I have a CCU plus anchor, 316 stainless steel, 3/8 inch diameter. You can see our tension load is 25%, shear load is 25%, overall interaction DCR is 20%. I'm using ACI 318/14 for basis of design. I do have seismic turned on and loads, category D, so this is in a seismic region. And as you see the loads here, 1,500 pounds tension, 750 pounds in shear. Now I go to comparison library.
And I am correlating the CCU with the SD6 power stud stainless steel and the headed hex bolt. I have different diameters, 5/8 inch and 1 inch diameter, which is much bigger than our CCU anchor. Our embed depths are slightly different. However, you see down here, tension load is lowest in our CCU plus. Our shear interaction, a little bit higher, but that's pretty good for a 3/8 inch diameter. Interaction overall, DCR 20% compared to 15% for headed hex bolt. So you can see the CCU is very effective, very powerful, even in its littlest state, 3/8 inch diameter. It performs almost as well as the inch diameter headed hex bolt, and it performs way better than a bigger 5/8 inch power stud SD6 wedge anchor.
So moving on to case studies. These are a few projects that I've worked on in particular. Last year, I was involved in a dam improvement project in the Pacific Northwest. And the challenge was they wanted to install a debris barrier kind of on the outer face of the dam to collect logs, debris, brush, etc., running down the river. So this would generate a high tension load, and they use steel cabling connected to a base plate. They wanted to find the right anchor solution on the dam wall for this application. Immediately, we knew that the best solution was using an undercut anchor. So we used the heaviest duty anchor that we have, well, one of them. We have a 16-inch long one, but a 3/4 inch by 14-inch long 3/16 stainless steel undercut anchor is our CCU plus. We use this anchor on this project. Here's a picture on the left, my colleague of mine going out to the site. And on the right side, this is the dam wall face. The dam was actually poured back in, I guess, the 1960s. It's up in Washington. It has river rock, Washington River rock aggregate in it. So I don't know if you guys know, but yeah, it's very, very large. The aggregate itself is very large, strong. So we estimated the PSI of the concrete to be about 7,000 PSI, give or take. Pretty hard to drill through, honestly. We use the standard drill bit instead of the hollow bit system. I guess it was contract to preference for standard bit. Not entirely sure, but we use the standard bit. SDS max bit, massive drill bit. We used our Stingray dust extraction vacuum, as you see here, kind of the suction cup on the sidewall. So that got all the dust out, silica dust, as we drilled through the river rock aggregate. Pretty large, that drill bit was kind of cut up afterwards. But they did four holes. We were out there to kind of be alongside them for the first round of drilling. They had 2 sections of the dam wall that they were drilling into. We were only present for one of them. So there's 4 holes on that wall. You see the holes are drilled out. The initial pad holes are drilled out there on the right. Moving along on the left, then the worker is using an undercut bit, carving out that cavity in the back of each hole. And then also we made sure to suck out the dust too after each drilling. You can see in the middle, they're using a sledgehammer. They're going the old school method for that setting sleeve. And that's not using a powered, it's not working with a roto hammer. It's working just physical labor, pounding that setting sleeve in. They actually had a tie with electrical tape, believe it or not. The worker out there tying electrical tape on the setting sleeve, as well as onto the little torque wrench that they had for setting that anchor properly. But they were able to set all 4 anchors there in this application. Pretty rough using that sledgehammer, but it was pretty cool to see. And on the right, the anchors are properly set to the proper embedment depth, which was 10 inches deep. So they were going 10 inches deep for that undercut anchor. So overall, pretty cool project out there. My first undercut anchor project that I worked on right out of the get-go, and it was one of the largest anchors in our catalog. So pretty cool to see. It's always good to start with the largest anchor, then work your way down smaller. So for this project, mass transit project in Northern California, there's a public transportation authority out here, need a reliable solution for attaching overhead electrical and telecommunication supports. They're using a lot of strut channel, 1 and 5/8" strut channels, different configurations, also using seismic bracing, using the strut channel itself. So we found a good solution for this problem because we need to meet conformance, compliance with the specs, and also under seismic design considerations. We used a 3/8" by 6" long 3/16 stainless steel undercut anchor. This is also good for weathering effects in environments prone to corrosion, or not prone to corrosion, my apologies. And so these anchors are going to be very effective, long lasting, for the duration of the longevity of the lifetime of the project that was intended for. Post-install method, the most easiest rather than a adhesive anchor. So on the left, we had site photos. One of my colleagues, we actually gave a speech to the transportation district workers and engineers. And then kind of similar to what I'm doing today with you guys, we went over the undercut process, installation process, the different bits, visually how to install. And then we had the engineers themselves actually designing the project, install the undercut anchor in a concrete block vertically downward, which is pretty cool to see. They got hands-on, kind of feeling out how hard it is to drill, how to set that anchor properly. It really helped them and helped them get a good visual, good understanding on the undercut process, and then for them to design in the future years other projects for the undercut anchor itself. We also went back out on site for this job some point in the summer last year, and we just kind of troubleshooted and also gave a little undercut refresher demo to the workers on site with the different bits and accessories. They're having issues with some of the installation processes, and also maybe the torquing of the nut itself a little bit. So we came out there, mitigated the issues, walked them through the process, took pictures and videos of the entire process. Got to see kind of real world application and overhead installation of undercut anchor, which is pretty cool. And as they are using these quite extensively. Here on the left, there's a strut channel, overhanging some pipe, and then there's also, it just depends on the project, but they also have electrical conduit cabling, cable trays, etc. These are just a few different instances of me taking photos of how the strut channel was built out and designed, and then but they all use the undercut anchor on the underside of the slab. So you see here, hollow drill bit, stop bit. So the hollow stop drill bit on the left connects to the HEPA vacuum, drilling initial pilot hole. The right is still drilling through. It is pretty tight spaces up there. He's going underside of the slab, drilling through. Now he's using the undercut bit, going through, making sure getting that cavity drilled out in the back of the hole. Pretty tight spaces in between those pipes, but able to make it work for where the strut location was. And then the last example was for a project in Utah, and the SEOR, Structural Engineer Record, required the general contractor to test 3 potential undercut solutions. This is actually a different base material that they're being drilled into, the anchors, and so it's a quartz monzonite base material, not typical concrete. And so we realized that a good solution would be the undercut anchor, 3/4 inch heavy duty, 3/4 inch by 16 inch long anchor, the biggest anchor that we have. And we were in competitive testing with other manufacturers on site, and so they ended up choosing us for the undercut solution itself. And the field engineering team, it wasn't me on this job, but the field engineering team provided proper undercut anchor installation, training, and performed shear testing on site, was there throughout the duration of the install. And this example is pretty much, it's a true testament to our field engineering services and undercut anchor performance. overall. So with that, I kind of leave some questions and answers, so that went 2 minutes over. But yeah, I'll give it back to you, Zach.
All right, excellent. Thank you, Lars. Really appreciate you presenting today. Yeah, as Lars mentioned, we still have around 12 minutes to go for Q&A. If there are any more questions, I saw a bunch of questions come in that we were able to answer, during the presentation. So we're happy to stick around and answer any more questions that anyone might have. And just to reiterate, your PDH certificates, we'll have those emailed out to you in the next day or two, and also a PDF copy of all the slides will also be emailed out as well. Yeah, I don't see any other questions coming in, so please type them in. If not, we are happy to give you back a few minutes of your day to get back to the real world. Here we go. Jason, would you like to come back on camera?
Sure, no problem.
All right, Jason, can you introduce yourself real quick?
Yeah,
Oh, perfect.
yeah, sure.
We got a couple couple of questions coming in.
I'll let you answer. There's an administrative one for our group, but the technical one I'll answer. So, all right, yeah, hi everybody, and good job, Lars. I'm Jason Wagner, Director of Field Engineering here at DEWALT. I've been doing anchors and fastening for most of my 16+ year career. So that's who I am. To answer the question, the CCU Plus is our latest product release in the undercut category. We launched it a little over a year ago, and it's a much more improved product with the performance values. We now have a stainless steel version of the product that's within our ICC report. So a lot of similarities, I would say, to the Atomic in the look and feel of the product, but with a lot more technical data and capability behind the anchor. It's certainly best in class in that category. And so that's the biggest difference between the CCU and the Atomic. The other thing I will say is, if you do have some of the installation accessories in the Atomics, you're familiar with that anchor, they're not the same as our CCU Plus. So for example, the undercutting bit does have a different angle. So if you want to make sure you're installing it correctly, you have to use the CCU Plus installation accessories. Okay, the next question here. What is the hardest concrete or the highest compressive strength that the bits can go through? Just to kind of frame how we test these anchors and really all post-installed mechanical and adhesive anchors, we start out with ACI 318 requirements, and the compressive strengths on the high end really top out for testing purposes at 8,500 PSI. So that's what's considered for per ACI high strength concrete. I will say that these the undercutting step to install these anchors is certainly sensitive to compressive strength of concrete or rebar, for example. We'll have trouble with rebar if it comes in contact with rebar, like most bits would. So there is some technique that goes into the actual undercutting step of the process. You have to be apply the right amount of pressure, not too much, not too little, to create that that undercutting hole. And that's why we actually do suggest, if you do design an undercut anchor and it's gets out to the field, that you call up a DEWALT field engineer or a local rep to come out and help with some installer training, because there's definitely I think some training would be helpful to install this anchor. Jason,
is the installer training required like it is with adhesive anchors?
No, it's a good question. It's it really comes down to what the engineer of record has specified in your construction documents. So if there is, we will see, based on the special inspection requirements, occasionally engineers will write into their specs or their notes a training requirement for mechanical anchors, for post-installed anchors. So if that does exist in the notes, then yes, we will come out and do training. That is different than an adhesive anchor certification. Just want to make that clear. Let's see. Radar imaging could be used to lessen the chance of hitting rebar. Yes, I think that's a comment rather than a statement. So yes, if you're doing, if you're scanning your concrete for rebar, then yes, absolutely that would help. And with all post-installed anchors, that's always an issue when you hit rebar. All right, another question. The Utah project, did I understand correctly that the anchor was installed into natural stone, not concrete? If so, was the same drill bit used or a special drill bit for the stone? So natural stone, we get a lot of questions for all sorts of anchors on anchor capacities or installation in natural stone. And the short answer is natural stone is there's a variety of different stones you can install into. And so there are a variety of different potential loads that can be established in natural stone. So we always recommend on-site pull testing or just verification of your base material. And so the second part of that question is on the same drill bits. Yeah, we use the same drill bits for these applications. If you're going into natural stone, that's very, very hard. Just like with a very high PSI concrete, you're going to run into issues. But in that particular case, our standard installation equipment was acceptable. All right.
Excellent.
That's it.
Looked like that cleared up the backlog of questions. Thank you, Jason, for hopping on, and Brent as well for answering questions as they came in. With that, I think we're going to wrap up this webinar. Once again, thank you everybody for attending and participating and giving us your attention over this past hour. With that, we'll log out, and thank you everyone. Have a good rest of your day. Thanks again, Lars.
Yeah, thanks guys.